So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to have Francis Nimmo, who's come across to us from UC Santa Cruz, across the hills. Francis got a BA and PhD from Cambridge, where he did his PhD on the volcanics and tectonics of Venus. He came across to work at Caltech for a short time in '99, and then joined the faculty at UCLA in 2002. And then in 2007 moved up to UC Santa Cruz. Also in 2007 he was the recipient of the Urey Prize and also the McElwain Medal for his outstanding achievements as a young investigator in the field of planetary sciences. Francis's interests revolve around structure, evolution, interior dynamics of planets and satellites. He is most well known for a number of things, including a method of tidal heating, inducing heat in the south pole of Enceladus, causing the tiger stripe activity and geyser there. He's also worked on the hemispheric dichotomy of Mars resulting from an impact, and plate tectonics linkages to planetary dynamos in the terrestrial planets. Today he's going to talk to us about the geophysical evidence for a subsurface ocean on Titan. So if you all join me in welcoming Francis.
Thanks, Adrian, for that kind introduction. What I'm going to talk about today is a couple of different ways of trying to probe the internal structure of Titan. And most of this work was done in collaboration with Bruce Bills at the Jet Propulsion Laboratory. So I'll give you a brief overview of Titan, and then the bulk of the talk will consist of two parts. The first part looks at the orientation of Titan's spin axis, and it turns out that you can actually tell something about what's going on inside just by measuring that quantity. And then the second part of the talk, which will be a bit longer, argues that we can use the long wavelength shape of Titan to infer something about its internal structure. And in particular, both of these lines of evidence suggest that Titan has a liquid water ocean somewhere beneath the solid ice shell. And one of the things that I'll do throughout this talk is just point out that even though I'm mostly applying these techniques to Titan, you can actually apply the same techniques to other places in the solar system, other icy satellites, and even elsewhere. So even though most of what I'm going to be talking about is relevant to Titan, these techniques are actually very generally applicable. So this is the playing field. This is the Earth's moon for scale, and these are the satellites of the outer solar system. Jupiter has 4 big ones. Saturn has a bunch of little ones and one big one, which is Titan. And then Uranus and Neptune have their own satellites too. Why do we care about them? Well, you just saw that there are a lot. There are many more than the terrestrial planets, and that's nice because one of the things that allows us to do is to distinguish between one-off processes that just happen once and processes that are universally important. Because we have statistics, we can start to identify which processes happen in many places. As you'll see, they look very different. Some are young and geologically active, some are ancient, they haven't really done anything for billions of years. And so they're surprisingly diverse, and they record a lot of history. And so by looking at their surfaces, we can try and piece together how they've evolved over billions of years. In some ways, they're intrinsically more complicated than the terrestrial planets. The thermal evolution of the Earth, how it cooled over time, doesn't care about the Earth's orbit. Those two problems are completely decoupled. But for the satellites, the main source of energy that keeps them warm actually is the orbital energy itself. And so to work out how icy satellites have cooled over time, you actually have to worry about their orbital evolution too. And so they're intrinsically more complicated than the silicate planets. We know now that many of these icy satellites have liquid water oceans beneath the surface. And so that's very important from an astrobiological point of view, because it suggests that at least in principle, there might be habitable environments out there. And finally, if we can understand these objects, then we can maybe apply that understanding elsewhere. For instance, to the Kuiper belt, places like Pluto. There may be super Ganymedes in other solar systems. And one of the things that I'll point about in this talk is that we may even be able to apply that, some of our understanding to our own moon. So you can take your understanding of the satellites and apply it elsewhere. Okay, well, zooming in on Titan, Titan is an extremely interesting object. It's perhaps the most interesting object of the satellites. And one reason is that it's unique among satellites that it has a thick atmosphere. And it's also, you know, it's about the same size as Mercury. And so it really is a world in its own right. Because of the atmosphere, there are all kinds of astrobiologically interesting compounds present. There are organic molecules, there are various kinds of hydrocarbons. And so in some ways, it has a lot of the prebiotic molecules that you could potentially make life out of. It also has an active weather cycle. It's not really a hydrological cycle, because the fluid, it's so cold at the surface that the fluid is liquid methane or liquid ethane. But as you'll see, you know, there are clouds, there's rainfall, there are river channels that get carved, and so it's very active at the surface. One of the reasons that Titan is exciting is that the Cassini spacecraft is currently whizzing around the Saturn system looking at Titan, and Huygens was this little probe that actually landed on the surface of Titan. One of the things that I'm going to argue, though, is that even though we know quite a lot about the surface, its internal structure is currently very poorly understood, and that's what I'm going to try and address in this talk. These are just some snapshots of the surface of Titan. This was an image taken by the Huygens probe as it parachuted down. And the really striking thing about this image is that it wouldn't look out of place on Earth. It's about 30 kilometers across, and you can see that there are these dendritic river channels. Now, Titan's too cold for those channels to have been carved by water, probably carved by liquid ethane and liquid methane. But you can see that there's certainly an active hydrological cycle on the surface of Titan, and that's very interesting. This is an image of the surface of Titan taken by Huygens after it landed. These cobbles are a few tens of centimeters across, and you can see that they're a bit rounded, and that's probably because they were transported down slope and they bashed into each other. So there are sedimentological processes on Titan, just like there are on the Earth. And then this image is a radar reflectivity image, and it's been colored in a cunning way to give you the impression that what you're seeing are lakes. And indeed, we think that there really are lakes there, even though that the color scheme is designed to make you think that way. But so there really do seem to be lakes on the surface that are made of liquid ethane and liquid methane. So there are channels that get carved, and the rain accumulates in lakes. So the surface of Titan is extremely interesting. Because there's this active weather cycle, the surface is very young. You don't see impact craters in many places, and that's presumably because they're just getting flattened out by sedimentary processes. It may be that there are tectonic features. It's not really clear, and that's again partly because the surface is getting resurfaced so fast by erosion. So in many ways, Titan's surface looks a lot like the Earth. In terms of its internal structure, we don't have very many direct constraints. We know that the surface is icy, and we know the bulk density of Titan, which means that the inside has to be denser than ice. It's probably some kind of a mix of silicates and ice. One of the things that we don't really understand yet is the extent to which the ice and the silicates have separated. There are now gravity measurements that I'll explain a bit more in a minute, and they suggest that the silicates and the ice haven't separated out completely. It looks like Titan is incompletely differentiated. There hasn't been a complete separation of the silicates and the ice. And that's a bit like the large moon Callisto. One of the things that we don't actually know is whether or not Titan has an ocean beneath the surface. Model predictions suggest that it should do. You should have low pressure ice and then an ocean and then high pressure ice beneath. that's a pretty common prediction amongst models, but we don't have any direct evidence that there really is a liquid ocean there. And of course, we'd like to know that from an astrobiological point of view, if nothing else. And so what I'm going to argue is that there are a couple of techniques that suggest the models are right, and there really is an ocean down there. Okay, so the first way of doing this is to look at the orientation of Titan's spin axis. And what this allows you to do is to get an idea of the moment of inertia of Titan. Now, what the moment of inertia means is just how is the mass inside Titan distributed. You can imagine that you could have two bodies which have the same bulk density, but one has a dense core and a light mantle, and the other one is homogeneous. Even though these have the same density, they would have different moments of inertia. And so the moment of inertia is a really useful thing to measure because it tells you how much of the mass is concentrated towards the center. This is the way that you would tell the difference between a body that's differentiated and a body that's not differentiated. So the moment of inertia tells you something about the internal structure of a satellite. Unfortunately, it doesn't give us any information directly about whether or not there's an ocean there, just because the density of the water and the density of ice, they're very similar. You can't tell the difference. Because we've managed to measure the gravity of Titan, as Cassini goes past Titan, it can measure the strength of the gravitational attraction. Because we've measured the gravity, it turns out we can actually tell what the moment of inertia of Titan is. This was done by Luciano Yes and colleagues. And that's why we think Titan is partially differentiated. It looks more like this. Everything's mixed up together. The silicates and the ices haven't separated out completely. So by measuring the gravity of Titan, we can actually tell that it's not partially differentiated. And so this is a very useful constraint. It tells us something about how Titan has evolved. Now, what Bruce Bills and I wanted to do was to use a different way of measuring that moment of inertia. And it turns out that just by looking at the orientation of Titan's spin axis, you can determine the moment of inertia. So the obliquity is this angle epsilon, and that's just the angle between the perpendicular to the orbit and the spin axis. So the Earth is tilted over on one side by 23 degrees or whatever. That's what obliquity means. Titan should also be tilted over on one side. And it turns out that there's a simple relationship between how tilted over it is and what its moment of inertia is. And so we thought, well, we know what the obliquity, the tilt of Titan is. We ought to be able to use that to calculate the moment of inertia. And so that way we can check the gravity measurements. So you can take the gravity measurements and you can predict what the obliquity should be. We did that, and then we compared it with the actual obliquity of Titan, which is that. And so there's a problem. The obliquity that you predict based on the gravity measurements is smaller than the value that you actually observe. And so our slightly hand-wavy explanation, and this is okay, but we'd like to understand it better, is that what's really happening is that when you're measuring the tilt, what you're really measuring is the tilt of the ice shell, which is decoupled from the interior by an ocean. And so the gravity is telling you something about the moment of inertia of the whole body, whereas this tilt is really just telling you about the tilt of the ice shell. And that way you can actually explain why the tilt is much larger than it should be. So we're arguing that the fact that the tilt is large is telling you that the shell is decoupled from the interior. That's the argument. If you care about the math, this is more or less what's going on. You may not care about the math, but let me go through it very quickly. So what you care about is the tilt, the obliquity. That depends on the orbital inclination, which we know. It depends on how fast the orbit is precessing, we know. And it depends on the gravity of Titan, which we've measured. And so the only thing that you don't know in this expression is the moment of inertia. And so you measure the obliquity, you get a moment of inertia. And if your obliquity is big, then your moment of inertia is big. And so this is the equation that I'm just plotting here in words. For obscure reasons, the thing that we're actually going to plot is this thing gamma gamma is big if the moment of inertia is small and vice versa. That's really just a detail. So here's the picture. This is just a plot of where the orbit perpendicular is pointing in the sky. And this is where the spin pole of Titan is pointing in the sky. And so the distance between them is the tilt of Titan's spin axis, the obliquity. So the obliquity is large. If Titan was behaving as a nice, solid body with a moment of inertia that the gravity told us, that's where its spin pole should be. And so the observed obliquity is much larger than the predicted obliquity. And so what you have to do is to say, well, the effective moment of inertia that we're measuring is bigger. And if you end up with an effective moment of inertia that's bigger, you can get a predicted value that's very, very close to the actual value. And that's why we're calling it decoupled, because somehow the shell is getting decoupled from the interior. And so what we're plotting here is just the misfit between the predicted position and the observed position as a function of this thing that tells you what the effective moment of inertia is. If you use the solid body value, you get a big misfit. And if you allow the shell to decouple, you get a much smaller misfit. Now, you can see here that the misfit, there is still a tiny misfit. It's not very big, but it's non-zero. And we think that the reason that's happening is that, remember, Titan has an atmosphere. And what Titan's atmosphere does is it couples to the surface, and so it can actually change the spin state very slightly. So I think the fact that you don't have a perfect match here is because the atmospheric circulation is actually slightly perturbing the satellite. One of the nice things about this model is that we can actually test it. In a decade, we'll know whether we're right or not. And the reason is that the spin pole isn't fixed in space. It's actually changing slowly with time. And the rate at which it's changing depends on the moment of inertia. And so this is where the spin pole is now. This is just a map of where it's pointing in the sky. And it's going to move over time. And if the gravity measurements are correct, then it'll be moving quite fast. If our decoupled idea is correct, it's going to be moving more slowly. And so all we need to do is to come back in 5 or 10 years' time and see whether the thing has moved to here or here. And that way we can distinguish between these two hypotheses. If it's moved somewhere over here, then we'll have to think again. But this is a testable prediction. That's very important. OK, so we can get a location of the spin pole that's very close to the actual observed value. But in order to do that, you need to have a moment of inertia that's much bigger than the gravity measurements would suggest. And we think that the reason that's happening is that the shell is decoupled from the interior, although we don't really understand how that decoupling works. The details are still obscure. We also think that the small mismatch that you still get is because the atmosphere is exciting the spin state very slightly. But we can sort of check this whole hypothesis by coming back in a decade and making more measurements. This is a testable prediction. So even though we don't really understand the details, it seems like we can reconcile all the observations as long as Titan's ice shell is decoupled from the interior by an ocean. OK, so that was the first piece of evidence suggesting that Titan has an ocean. Before I go on to the second piece, I should tell you that you can do this trick elsewhere. Vesta and Ceres are two large asteroids, and they're interesting because the Dawn spacecraft is going to be paying them a visit. And I'm not going to go through all the details, but this is just another map of where the spin pole should be and where it actually is for both Vesta and Ceres. And again, you can see that there's a fairly big mismatch. Now, the measurements are pretty bad right now. There's a lot of scatter in the observations. And we don't know very much about what the gravity of Vesta and Ceres is. And so at the moment, I don't think there's very much that we can say quantitatively. But it looks to me as if there's a big mismatch between where Ceres' spin pole should be, where it is. And so maybe the shell of Ceres is decoupled from the interior. And once we get the measurements back from Dawn, we'll be able to do this job properly and really say something interesting about the interiors of these asteroids too. Okay. The other thing I want to talk about is how the ice shell of Titan sitting on top of the ocean might behave. And in order to do that, I'm just going to spend one slide talking about tides. So here is Titan, and it's orbiting around Saturn. Saturn is a big mass, and Titan has a finite radius. So a point here is experiencing a slightly larger gravitational attraction, and a point here is experiencing a slightly smaller gravitational attraction. And so what tides do is they end up deforming you. A satellite orbiting a big planet is going to be deformed. It's going to get stretched like that. And in fact, because it's rotating as well as being tidally stretched, it ends up having this peculiar shape where all three axes have different lengths. It's squashed at the poles, and it's pulled out towards Saturn. So the shape is controlled by tides, but tides also control the energy. And the reason is that if your orbit isn't quite circular, then at some point you're close to the planet, and at another point you're far away. And so the tidal bulge is going to get bigger and smaller and bigger and smaller, like that. And if there's any kind of friction in the system, then some of that mechanical work gets converted to heat. And so tides are a way of heating up your satellites. And of course, in extreme situations, you end up with somewhere like Io. This is a picture of Io, and this is a volcanic fire fountain blasting stuff 400 kilometers into space. So tidal heating can produce enormous volcanic activity. Okay. Well, what we want to think about is how tidal heating affects an ice shell which is floating on top of an ocean. And it turns out that the tidal heating isn't constant. It actually changes with position. And in particular, you get more tidal heating towards the poles and less tidal heating towards the equator. And so if your shell is conductive, then if you're heating it more, it'll end up being thinner. And where you're heating it less, it will be thicker. So you would expect to see variations in the thickness of the shell as you move around the satellite. And so if you have a shell that's thin in some areas, then those areas are going to be low. And where the shell is thick, those areas are going to be high. Just like on Earth, the oceans are low because the crust is thin, and the continents are high because the crust is thick. It's the same principle here. So you should have topographic highs at the equator, topographic lows at the poles. One of the things we've done is to measure the topography of Titan. And this is a map of Titan's topography. And you can see that it's low at the poles and it's high at the equators. And this is quite a big range of relief. It's about 1 kilometer from the highest point to the lowest point. So Titan is not completely smooth. It has some topography to it. The interesting thing is that you can predict how big those topographic variations should be based on what we know about its internal structure and the gravity. And the pattern is about right, but the observed amplitude is larger than what you'd expect. It's larger by a factor of, say, 2. So Titan has unexplained topography. It's too high around the equator, and it's too low around the poles. So it's higher at the equator than you'd expect, and it's lower at the poles than you'd expect. And so we want to try and explain why that should be. One possibility is that you made Titan closer to Saturn, and if it's closer to Saturn, it's more deformed. And so you take that more deformed Titan, and then you move it further away. That would be a way of having a bigger bulge at the equator. But if you did that, you would generate whopping gravity anomalies that you simply don't see. And so that explanation can't be right. What we suggest is that you have shell thickness variations which give you extra topography at the equator and a deficit in topography at the poles. So this works in the following way. Remember that there's more tidal heating at the poles and less tidal heating at the equator. If you thought that your shell had the same thickness everywhere, maybe the shell was convecting and keeping the shell thickness constant, then you'd still have warmer ice at the poles and colder ice at the equator just because of the tidal heating. And so that would give you warm ice expands, and so you'd have a topographic high at the poles, a topographic low at the equator. On the other hand, if you make your shell conductive and you have shell thickness variations, then where there's more heating, you'll have a thin shell, you'll have a topographic low. Where there's less heating, you'll have a thicker shell, you'll have a topographic high. So these two scenarios give you opposite signs, which is nice. That means that, you know, as long as your observations are even slightly good, you can actually tell the difference between them. And remember that the observations tell us there's more topography than you'd expect at the equator and less at the poles. And so it looks like this is the right idea, that there are variations in the thickness of the shell. So that's the kind of cartoon that if there are shell thickness variations, then we might be able to explain the topography that we actually see. Again, if you care, you can stick some equations in. All I'm doing here is I'm balancing the diffusion of heat against the tidal heat production inside the shell, and you end up with a temperature profile that looks something like this. You're generating heat inside the shell because of tidal heating. You're putting some heat into the bottom of the shell too. So we care about the heating, and that depends on the tidal strain. And the tidal strain, it varies with position. It cares about things like the eccentricity of the orbit. The most important thing it cares about is this funny thing called the tidal love number. And the tidal love number just tells you how deformable the body is. A big love number means that it deforms a lot. A small love number means it doesn't deform very much at all. So the tidal heating looks something like this. You get more tidal heating at the poles, less tidal heating at the equator. And what you do is you take this map of the tidal heating, and that allows you to predict how the shell thickness varies, and that allows you to predict the topography, and then you can compare the topography with what we actually see. So you can make a model of what the topography should look like. You can compare it with the observations. Just let me explain about love numbers. They're called love numbers because the guy who invented them was Mr. Love. Okay, just to remove any confusion. So there are two kinds of love numbers. The long-term shape of a satellite depends on what's called the fluid love number. That just tells you how deformable it is. And we actually know what that love number is because we've measured the gravity. But there are also tidal love numbers. And tidal love numbers tell you how it responds to the tidal forcing, which happens over, a few days. So fluid love numbers give you the long-term shape. The tidal love number tells you how much it responds to the short period tidal variations. Okay, here are some results. What I'm plotting is the misfit between the model topography and the observations. And the first thing I'm doing is I'm going to vary the fluid love number, and I'm not going to worry about shell thickness variations. So all I'm doing is I'm changing the global shape of Titan. And what you can see is that if your love number is small, then the misfit is large. As you make your love number bigger and bigger and bigger and bigger, then the misfit gets smaller. And that's because we need to have a Titan that's more distorted. The problem is that to get a really good match, you need a love number of about 4, and it turns out that's physically impossible. You can't do that unless Titan is hollow on the inside or something. And in any case, we've measured what the love number of Titan is, and we know it's this value. And so you end up not being able to get a good match between the observations. The mismatch is still large. So just having a tinily distorted Titan doesn't give you a good fit. And so instead, what you can do is you can add in shell thickness variations. The shell thickness is varying because the tidal heating is varying. And so now I'm plotting the misfit, and I'm varying the tidal love number. And the tidal love number is telling you how important tidal heating is, basically. And what you see is that you can get a nice low misfit value, and the tidal love number that you need is pretty much what you'd expect from models. We haven't measured the tidal love number, but you'd expect to get a value somewhere in here. And so you can get a nice match to the observations with a tidal love number that sort of makes sense. This is just a summary of the results. What I'm plotting is the best fit models as a function of this tidal love number, and also how much heat I'm putting into the bottom of the shell. There are different lines because I can make different assumptions about how stiff the ice shell is. And the details don't really matter terribly much. But what matters is that for reasonable guesses at what the tidal love number is, you can work out what the thickness of the ice shell should be. That's what these colors represent. And you can work out how much heat is coming into the bottom of the ice shell from the silicate interior. So you end up with an ice shell thickness of something like 100 kilometers, and you end up with a heat flux into the bottom of these funny units, 5 milliwatts per meter squared. I'll tell you what that means in a minute. The absolute value is not very important. So this is just a plot of the best fit model and the observations. You can see that the amplitude of the topography is about right. The pattern doesn't match terribly well, but this is partly because there weren't very many altimetric profiles used to generate this topography. I've actually seen a more recent map that looks much more like the model predictions, so that's nice. The observations are now coming into match with the model. The thickness of the ice shell that you get is about 100 kilometers, and that's again something that we can test. As Cassini gets more gravity observations, we can actually test whether that's correct. We know how much heat is going into the bottom of the ice shell, and the absolute numbers don't really matter, but if you took a silicate titan of the sort of standard solar composition and said how much radioactive heat was coming out, you get almost exactly this number. And so that's a nice reality check. The other important thing is that the radioactive heat production is much more important than the amount of heat that's being dissipated in the ice shell. The amount of heat that's being dissipated in the ice shell is quite small. It's a sort of a tenth of this background value. And the reason that's important is that it means that Titan's orbit is evolving very slowly. It's not one of these satellites that's zooming in towards Saturn. It's only evolving very slowly because the tidal heating is small. OK, so for this model to work at all, you need an ocean. And so that's really the top-level message, that if this is correct, Titan really does have an ocean down there. The ice shell on top of that ocean, though, must be static. It can't be moving because you have to retain these lateral variations in shell thickness. And so that means that the ice shell is not convecting. It's not moving. And that's surprising, but the way you explain that is by having an ocean that's very cold. If the ice is really cold, it's so rigid it's not going to convect. And the easiest way of doing that is to stick a lot of ammonia into your ocean, because ammonia is a really good antifreeze. It'll stop the ocean freezing till it gets, 100 degrees C below what we would normally think as the melting temperature of ice. So ammonia is a good antifreeze. Even if the ice shell is not convecting now, it may have been convecting in the past, and that's because we can tell how much argon there is in the atmosphere, and argon comes from the silicates. And so somehow you have to get that argon from the silicates to the atmosphere. And it's hard to see how you could do that if there's this 100-kilometer thick layer of ice that's not moving in between. So it seems likely that even if that shell isn't moving now, maybe it was convecting in the past. One of the cute things about variations in shell thickness is that they can actually make the whole satellite unstable. The shell every so often can flip through 90 degrees. And so this is kind of dramatic. Unfortunately, it doesn't work for Titan. And the reason is that Titan's atmosphere redistributes heat, and so it actually changes the pattern of shell thickness variations. And so Titan's shell is stable, whereas somewhere that doesn't have an atmosphere like Europa, that shell really can go through 90 degrees reorientations every so often. So that's more or less a detail. And the rate of orbital evolution is slow just because there's not much dissipation in the ice shell. Okay, so the first half of the talk was looking at Titan's spin state, and the tilting of Titan is larger than you'd expect. And we're arguing that that large tilt can be explained if the shell is decoupled from the interior by an ocean. The second half of the talk looks at the shape of Titan, and in particular the fact that it's fatter around the equator than it should be. And we can get a reasonable match between the observations and a model in which you have a shell thickness which varies in space floating on top of an ocean. And that model has various other implications, like the fact that the ice shell can't be convecting now, but it may have done in the past. And the absence of convection in the shell is probably because the ocean is ammonia-rich and cold. Just to finish up, I wanted to remind you again that these techniques can be used in other places. And so one place that we think about a lot is Europa. Europa is a satellite in the Jupiter system, and it probably is similar to Titan. It's a bit smaller. It has a metallic core, a silicate interior, and then a rather thin, couple of 100 kilometers, H2O layer on top. One of the things that we don't know is how thick the ice shell on Europa is. It's certainly thin. It might be a few kilometers thick. It might be a few tens of kilometers thick, but it's definitely thinner than Titan's ice shell. You can do more or less the same trick for Europa, which is to look at the surface shape and see whether there's any evidence for variations in the thickness of the shell. Unfortunately, for the European system, we don't have an altimeter, but what you can do is to take an image of the limb of the satellite. In this case, this is Mimas. And so you digitize that image, and the bumps that you see on the limb, you convert into topography, right? So you can actually measure the topography just by taking an image. Now, Galileo was not a very happy spacecraft, and so for Europa, we only have 4 limb profiles. But still, we know something about the long wavelength topography of Europa. And so here are those limb profiles. So this is just radius and latitude. And the dots are the individual measurements. And you can see that Europa certainly is distorted. It has long wavelength shape. The solid lines are the best model that we could come up with that incorporated variations in the shell thickness. And you see that it doesn't do a very good job of matching the observations. The really sad thing is that a much simpler model with no shell thickness variations at all does a better job of fitting the data. So you went through all this work to put in shell thickness variations, and it turns out that the fit you get is worse than the simple model. So that was kind of annoying. So there is no evidence at all for shell thickness variations on Europa, which is sad. But what's interesting is that you can argue it 2 ways. Either you have a very thin shell, and so the variations in the shell thickness that might be there are just too subtle to detect. If that's true, then that means that Europa's pumping a lot of heat into the base of the shell to keep it thin. So it might be that Europa's shell is very thin, only a couple of kilometers. And that's exciting because it means that the ocean is very close to the surface. On the other hand, it might be that the shell is very thick, because if the shell is very thick, then the ice at the bottom of the shell can flow laterally and remove shell thickness variations. And so the sad part of this talk is that you can't actually tell the difference for Europa between a thin shell and a thick shell. But all is not lost, because if we ever get round to sending a spacecraft back to Europa, then what we can do is do a proper job of measuring the topography using an altimeter, and that will then tell us whether we're in a thick shell or a thin shell regime. So even at Europa, we can do things if we have a better spacecraft.
Francis, 35 kilometers is a thin shell?
Mm-mm.
Okay.
It's
The thin shell is thicker than the thick shell, which is 30.
I can't say anything about the shell thickness for Europa.
Okay, you had hinted that it was only a few kilometers that you were spoken.
That's right, and some people believe that, and I am agnostic on it. The other place that I wanted to mention was Enceladus. Enceladus is small. It's about the size of the United Kingdom, but it's very interesting because it's geologically active. This is a picture of what the inside of Enceladus might look like. It has a silicate interior and then an ice shell. We don't know whether or not it has an ocean there. If you look at the surface, you can see that some areas are heavily cratered and old, and some areas are uncratered and therefore very young, and they also have these funny tectonic features called the tiger stripes. And of course, the tiger stripes at the South Pole are the source of geysers. These are ice particles being blasted off into space by geysers. And if you sort of unstretch this image, you can actually see the individual plumes of material coming off. So Enceladus is geologically active. One of the things that I've been doing is trying to measure the shape of Enceladus using these lines are limb profiles. And so the colors and the contours give you the topography. And again, Enceladus is quite bumpy. It has, you know, more than a kilometer of relief. What I'm showing you at the bottom is a different way of getting topography. This is from stereo imaging rather than limb profiles. It's a very different approach. But what you can see is that where they see deep holes, A, B, C, and so on, I tend to get low areas. And so that gives me a certain amount of confidence that both of these things are telling you more or less the same story, which is nice. It's nice to check that your measurements are actually real. So Enceladus is bumpy. You know, there's kilometer scale relief at long wavelengths. And you can't do that if the ice shell is convecting. You can't create a kilometer of a mountain by convection in the ice shell. And so I think that at Enceladus too, there may be shell thickness variations going on. And so that's something that's a sort of active source of research right now. The last place I wanted to mention was the Earth's moon. And you've seen this picture before. You have a liquid layer with a shell of variable thickness. Before I was talking about ice and water. For the earliest moon, this fluid would have been molten magma, and the solid would have been the silicate crust that was solidifying. But exactly the same logic applies. Where the shell is being heated more, where the crust is being heated more, it will be thin. Where it's being heated less, it will be thick. And so on the early moon, while it was being tidally heated, when it was close to the Earth, you end up with thick crust and thin crust, high topography and low topography. And if you compare these model predictions with the observations, you can see that in the lunar highlands, there's actually a reasonable match between the model predictions and what we actually know about crustal thickness variations on the moon. And so it may be that some of the moon's structure was formed very early in its history when it was being tidally heated, when it was close to the Earth. So icy satellites can tell us something about our own moon. And so I'll just leave you with my conclusions. There are two observations. Titan is tilted over more than you would expect, and Titan is fatter around the equator than you would expect. And what I've argued in this talk is that both these observations can be explained if Titan has an ocean beneath its ice shell, and both these models make predictions that can be tested with future Cassini observations. And so in 5 or 10 years' time, we'll know whether or not these ideas are right. And so I'll leave it there. Thank you.
Thanks, Francis. Can I ask the first question, and then I'll get to Jeff? Would you expect to be able to detect such a subsurface ocean using a magnetometer?
Okay, so the reason that we know there are oceans in the Jovian satellites is because Jupiter's magnetic field sweeps around. And if you have a changing magnetic field with a conductor like salty water, then you get magnetic induction, and that is something a satellite can detect. So changing magnetic field, conductive ocean, you see a magnetic induction effect that's measurable. The problem with Saturn is that the magnetic field is not sweeping around. Jupiter's is offset from its spin axis, so it does this. Saturn's is aligned with the spin axis, and so the magnetic field isn't changing. and so there's no induction effect. And so it would be lovely if you could, but you can't.
Francis, you mentioned that the argon-40 is evidence that Titan may have convected in the past. Now, I'm sure, as you know, Bill McKinnon has proposed that all this argon-40 could be there simply as a consequence of the late heavy bombardment. Do you agree? We haven't had a chance to talk about this. So do you agree with that possibility, or do you think that perhaps you would need to have a bit more convection and outgassing than the late heavy bombardment to explain the present argon-40?
If I can find a way of not having the ice shell to convect at all, that would make me happy. And the reason is that if the ice shell is convecting, then it's much more dissipative. And if it's much more dissipative, then that means the eccentricity has been damping much faster. And so that means the eccentricity back in time had to be very high. And you start to end up with uncomfortably high eccentricities at the start. So if you had an ice shell that was always conductive, that would actually be, I'd be very happy with that, as long as you can explain the argon some other way.
So you would be happy with Bill's result. Have you looked at this?
I haven't looked at the numbers. I mean, you can't do it too early because the argon takes time to build up, and so you probably have to tune exactly when you want that argon to be released.
Well, that's why everybody likes the late heavy bombardment. You give the place 500 billion years to get rocking, and then you crank out the argon-40, then you shut it down, and it stays undissipative, and you keep the present eccentricity and live happily ever after.
Yep. It would probably work, but I haven't done the numbers myself.
Okay, I'll let others.
It wasn't clear from the talk whether you, to figure out the surface thickness variations, whether you actually put in the atmosphere in the model. You mentioned the atmosphere at some point later, but
right.
Initially.
So the point of the atmosphere is that it keeps the surface temperature almost constant. I actually put in a small variation from equator to pole of 4 kelvins, which is about what's observed. But the point is that's very different from somewhere like Europa, where there's a 40 or 50 Kelvin temperature difference between the equator and the poles. And the reason the surface temperature matters is because that's one of the things that controls how much the shell thickness varies.
What observations and data analysis do you use to deduce the pole positions to such precision? I noticed a very small error circle that allowed you to make statements about the atmosphere.
Right. So what happens is that you take images of the surface at different times, and those images overlap. Now, you know where the spacecraft is, and you know the time that those images were taken. And so what you can do is you can solve for the spin state of Titan that makes those images overlap in the correct way. So that's essentially how it's done. It's not something that I do myself, but given enough images, you can get a very precise determination of where the spin pole is oriented because the images have to overlap correctly.
In this case, radar.
That's right. Yeah, radar, not optical. So the intrinsic resolution is limited by the resolution of the images, ultimately.
If there is such an ocean, are there any other candidates for the liquid besides water mixed with a lot of ammonia?
It seems hard to escape the idea that there's liquid water down there. If you need to have a cold ocean, there are things that you could add other than ammonia that would probably work as an antifreeze. For instance, if you put chlorides like salt, then that would certainly help to get a cold ocean. The reason that people appeal to ammonia is because it's thought to be present in large quantities in the outer solar system, but it could be something else.
On one of your graphs, you said that 160 meter RMS misfit is good, 240 is bad, and no misfit at all is unspeakable. Could you speak to it?
Well, Titan is obviously more complicated than just something that's tidally and rotationally distorted. I think a lot of the misfit comes from the shorter wavelength features that shouldn't appear at all in the simplest model. And so I can't explain things like mountain chains or impact basins. And I think that's where some of the misfit comes from. if you want to go with a worse Misfit, that's fine.
Okay, I was just wondering why you picked 160 as good.
Well, it's better than the one without.
Okay.
You certainly didn't mention much about temperature and pressure and the stability fields of liquid water and solutes. Could you expand a bit upon that topic?
Yeah, sure. So really the critical thing is that water has this very peculiar phase diagram which gives you low pressure ice that's less dense than water and high pressure ice that's more dense than water. And so under the lightly pressure and temperature conditions of Titan, you're going to have this ice sandwich with any liquid water that's present in the middle. In terms of the temperature of the ocean, if you stuff in as much ammonia as you want, you can get the melting temperature, the temperature of the ocean from 270 Kelvin down to 170 Kelvin. So if you really stuff a lot of ammonia in, it's an enormously effective antifreeze.
I understand that, but what are the numbers? What is expected? What are the pressures and temperatures that are?
So 10 to the 800 megapascals, give or take, at the base of the ice shell.
That's one ice shell.
Yeah, at the base of the shallow ice shell, 100 megapascals.
And temperature?
Could be anywhere from 270 if it's pure water to 170 if it's the, yep.
There's enough heat.
Well, it's not that there's enough heat, but that's why people like ammonia. Ammonia is a very effective antifreeze.
I understand that.
Yep.
Final question, what sort of thickness over the ocean are we looking at for the layer of ice? And would there be any possibility of communication with the surface?
So it's 100 kilometers thick, give or take. I think you'd have to be pretty optimistic to think there was any communication. So it's a very different situation from Europa, where you could argue that there might be communication directly between the surface and the ocean. Enceladus and Europa, I think it's reasonable to argue there is direct communication. Titan, it seems really hard.
What's the possible thickness for the ocean?
Oh, probably also 100 kilometers with an uncertainty of 2, something like that. So the ocean and the ice shell are comparable in thickness, whereas at Europa, the ocean is very much thicker than the ice shell.
Okay. Well, if you have any further questions, I encourage you to approach the speaker after the talk. Francis, we have a memento of your talk here today.
Thank you very much.
So join me in thanking Francis for his great talk.
Thank you.